Thank you for taking the time off today to join us for this webinar. My name is Karen from the Energy and Environment team in IPI. Today, I'm excited to present you a good lineup of speakers who will be sharing markets and technology insights in industrial wastewater treatment, challenges faced in implementing advanced wastewater treatment processes as well. There will also be technology providers who will be sharing more about their technologies and collaboration opportunities that they are seeking for. I'd like to take this opportunity to thank our partners who have helped to make this webinar possible. Imagine H2O for introducing the water tech startups, PUB and Enterprise Singapore for promoting this webinar to their partners as well as industry players. Just a little housekeeping before we get started. If you have any questions during the presentation, please type them in the question box. We will run through all those questions at the end of all the presentations. So I'd like to kickstart this session with a brief introduction on IPI and some of the platforms that we've developed to help companies to leverage on open innovation as a business strategy to develop new products and solutions. Let me share my screen. Okay, so increasingly more and more corporates are adopting open innovation as part of their business strategy, including government agencies as well. In fact, I think about 1 or 2 months back, PUB was they launched a global innovation challenge, looking at seeking for solutions that can address some of their operating issues. So a lot of companies are see the importance of open innovation because they start to realize that it makes a lot of sense to work with partners who have got expertise or technologies that they don't have to complement them in rolling out, in adopting technologies or rolling out products in the market at a faster rate compared to reinventing the wheel or developing everything in-house. So just some information about IPI. We are a non-profit organization funded by the Ministry of Trade and Industry. We are also a subsidiary of Enterprise Singapore. Our main mission is to help enterprises to grow their businesses through technology and innovation. So we focus a lot on industry needs where we work with enterprises to look for technologies that are not just in Singapore, as well as overseas. So hoping that we could facilitate partnership to bring new products and services to the market. So myself and my colleagues are from the Energy and Environment cluster, but within IPI itself, we have got a team of technology managers who have got domain experts in many different industry and technology areas. So we've got different teams that engage companies from different industry sectors. So we have a team from Infocom and electronics, another team in personnel and healthcare, another team in food, manufacturing, and materials and chemicals. So in terms of how we facilitate innovation, there are various ways in which we do that. One is through one-to-one engagement with companies in which we offer our innovation support services. For example, we have customer technology scouting services, which we offer for some companies. We also help companies to do out reports such as pattern landscape studies or technology landscape studies, where it gives them a very good overview of a specific technology area which they may want to adopt or they may want to invest. So what we do is we help them go deep dive into that topic and also help them uncover potential competitors as well as potential collaborators that they can work with. So we also have various digital platforms, which I will share in the next couple of slides. In terms of events, we regularly organize technology matching events where we showcase technology providers as well as bring together technology seekers in these events. So Tech Innovation is a flagship event that we organize every year. I'll talk about this in the next couple of slides as well. And all this is actually possible through the global innovation network that we have built over the years. We're part of the Enterprise Europe network, which is the world's largest innovation and business support network. We also have good networks to innovation nodes in different parts of the world, in Asia, Middle East, North and South America as well. So This is our online portal. I think some of the audience here might be very familiar with this because you receive our weekly newsletter Tech Alert, where we showcase new tech offers as well as new tech needs on our weekly newsletter. So our online portal is a good showcase of technologies from our various partners who are looking for commercialization opportunities. So in total, we have about more than 2,900 technology offers on our website, of which half of them are from Singapore and half of them are from overseas. Many of these technology providers are research institute, universities, startups, even large corporates that have got IPs that they want to they want to monetize and find potential collaborators to commercialize the technologies. And over the years, we have been running our portal for many years, and so we do have pretty good tractions on our portal. So we do receive a lot of inquiries on our portal on a weekly basis, which we track as well. So one feature which we have in our portal is that we have this feature called Tech Bundle, which we curate a list of technologies that allow enterprises to access, license, co-innovate with technology providers. So one example that I am sharing with you is the Water Tech Bundle. This is actually done in collaboration with PUB. So many of the PUB projects, many of the projects that are funded by PUB are actually listed on this portion. And we've curated this list of technologies, including and created different teams which we think would be of interest to the industry. So the various teams include water treatment, municipal wastewater treatment, industrial wastewater treatment, digital solutions, energy efficiency, and infrastructure. So if you're a company that's interested to look at technologies in this area, feel free to visit our Tech Bundle site and make an inquiry on our portal. If you have a technology that you would like to seek commercialization partners and you fit into any of this team, feel free to reach out to us as well. We're continuously trying to populate more and more relevant technologies in our Tech Bundle. So over the years, from our conversation with companies, we come to realize that companies don't just look for technologies. Sometimes they are looking for technical experts who could support them in their innovation projects. So what we have done is we've developed a tech expert portal, which is a one-stop technical expert matching platform for industry to self-help and find potential experts that they can work with in their innovation projects. So Tech Innovation is IPI's flagship event. This is an event that we run every year where we bring together technology seekers and technology providers on a physical marketplace. So the key feature of Tech Innovation is that we will bring in large corporates. For example, in previous years, we have got companies like Shell, BP, Coda, and this year we're going to have many corporates as well to share with us their technology roadmap as well as the type of innovation partners that they're looking out for. And also at the same time, we will be exhibiting and featuring technology providers who have got technologies that are looking for partnership, either test bidding opportunity or commercialization opportunities as well. This year, Tech Innovation is going to be held from the 7 to 11 December. Unfortunately, this is going to be different. We're going to hold it in a digital format because of this pandemic. So if you're interested in to participate in this event, feel free to register. The link is below. So all this are actually possible. So our connections, so sometimes people ask us, how are you able to reach out to so many different technology providers in different parts of the world? All this is actually possible through our wide connections with different partners in different parts of the world. And this includes the startup communities in various countries, the local and overseas academic partners, trade associations, government agencies, as well as IPI equivalents in different parts of the world. So the Emerging Technology Forum, as a new initiative which we launched last year, where we focus a lot on sharing market and technology insights on topics that are relevant to sustainability. because we do see there could be business opportunities in this area. So we thought that we'll pick out a few relevant topics to share on a yearly basis. So last year, we started off by sharing insights on battery recycling opportunities for electric vehicles. 2 months ago, we launched an emerging technology forum on indoor air quality. And then today, we're going to focus on the topic on very hard to treat industrial wastewater, which are typically from petrochemical industry, as well as pharma industry as well. So in each emerging technology forum, we will organize an event like now where we share some insights with the participants. Also, we will be launching white paper on some of our findings as well. So you can click on the links below to download the white paper on battery recycling as well as indoor air quality. We'll be launching the white paper on industrial wastewater treatment in 2 weeks' time. So the recording of our forums will also be available on our YouTube channel. So be sure to subscribe to our YouTube channel for more if you want to view the recordings of some of these forums. We also have, so some of these are just snippets of the kind of analysis that we've done on the market as well as technology. We also have full technology landscape reports, which we share more details about players in the entire supply chain, who are all the players, where we map up the entire landscape as well as providing more information on the pattern landscape. If you'd like to have access to some of these landscape reports, feel free to contact us directly. Okay, I've come to the end of my presentation. So I'd like to leave my colleague Ethan Siu to share with you more about his presentation on industrial wastewater treatment. So over to you, Ethan.
Thank you for your kind introductions, Karen. Good afternoon, everyone. My name is Ethan from the Energy and Environment Cluster. And today I'll be sharing with you some insights on industrial wastewater treatment. Specifically, we'll be looking at industrial wastewater that are hard to degrade by conventional means. We'll start off by first looking at some of the market trends and drivers in industrial wastewater treatment segment and the challenges associated with treating them. We'll then have a look at advanced oxidation processes for wastewater treatment and understand how these technologies may address these challenges. Finally, we'll take a quick glimpse at the patent landscape of advanced oxidation processes and chart a way forward to treat these wastewaters. Without further ado, let us first dive into the market trends of industrial wastewater treatment. Well, it's not possible to talk about wastewater without first talking about freshwater use. In the year 2010, approximately 3.9 trillion cubic meters of water is withdrawn for use. Majority of the water actually goes into agriculture for irrigation, while a sizable amount goes into industrial activities. 624 billion cubic meters of water ends up as industrial wastewater, and this value is expected to double by 2025. Right here in Singapore, the situation is similar. The water demand is set to double from 600 million cubic meters in 2016 to 1.2 billion cubic meters in 2060. Non-domestic water, including water for industrial use, will grow from 55 to 70% in the same period. With the rise in water demand and wastewater generated, the market will see a strong cumulative annual growth rate at 5.8%. The Asia-Pacific region is projected to be one of the fastest growing markets, growing from 40% from 2019 to 2024. This growth is due to growing population, rapid industrialization, and tightening discharge regulations in Asia. So how do we manage all this wastewater? We can actually take some reference from the general waste management framework. When possible, avoid generation of wastewater through segregation of wastewater streams or substitute the carbon raw materials with greener alternatives. Low-strength wastewater with low level of contaminants are relatively easy to treat and should be recycled and reused when possible. Mid to high-strength wastewater with heightened levels of contaminants can be challenging to treat and are required to be treated to a level fit for discharge as per the local regulations. If treatment is not possible, the wastewater will be sent for incineration. However, this comes at high logistical and management costs. Let us look at an example of how water is managed in Singapore's petrochemical and chemical industry. Bulk of the wastewater is generated by cooling towers and boilers. They are relatively clean and can be recycled rather easily. While the processed water takes up a small proportion of water used in the industry, the wastewater generated has high levels of contaminants and requires extensive treatment before it is fit for discharge. We have seen what are the market trends in the industrial wastewater treatment sector. In this section, I'll be sharing with you some other drivers moving these trends. There are essentially three key drivers for the industrial wastewater treatment market: the rise of industrial activities, tightening discharge regulations, and increasing environmental pollution awareness. First, we look at how industrial growth of key polluting industries give rise to more wastewater. The petrochem, textile, pharmaceutical, and paper industry are projected to see strong cumulative annual growth rate in the near future. However, things have changed significantly since COVID-19. Restriction of population movement have kept many people in their homes. Correspondingly, the energy demand for transport and commercial buildings have also fallen drastically. For all the viewers watching this at the comfort of your own homes, I'm sure fashion has taken a backseat since the pandemic. At least for me, the only purchase I've made in the last few months were a few comfortable t-shirts. It is not exactly all doom and gloom for all industries. There are still some bright spots. The pharmaceutical industry, for obvious reasons, have seen surges in their sales as all of us scramble to try and manufacture vaccines and COVID-related drugs. During the pandemic, the paper industry has successfully pivoted to making hygiene and medical-related products due to the increased demand. Next, we look at some of the discharge regulations and related measures around Asia. Southeast Asia's largest economies, Indonesia, Thailand, and the Philippines, have seen their fair share of non-compliance for industrial effluent discharge. And this will continue to be a challenge for local regulators as the countries continue to invest in basic water and wastewater infrastructure to make up for the shortfall. In Singapore, PUB has ramped up efforts to detect and fine illegal effluent discharge, and tariffs are in place for discharge exceeding the regulations. Looking beyond Southeast Asia, let us examine the situation in China and then in India. Before 2015 in China, there were little incentive for the polluters to recycle and treat wastewater, as the water prices and discharge fees are low. On January 2015, the Environmental Protection Law was revised to impose stricter fines and penalties. Enterprises were also named and shamed for environmental violations. In India, the effluent discharge of heavy polluting industries are constantly monitored at real time by the Pollution Control Board. The factories have to meet the discharge standards or face immediate plant shutdown. Finally, let us look at a shift in mindset among investors and general public towards environmental pollution. Investors are viewing practicing sustainability as a means to mitigate risk due to increasing regulatory and climate change. Likewise, the consumers are demanding enterprises to adopt sustainable practices in their manufacturing process. In response to that, the fashion industry has banded together to form Zero Discharge Hazardous Chemicals, a foundation founded in 2011 by various players in the apparel supply chain to eventually eliminate any waste discharge during the manufacturing process. At the minimum level, the Foundation seeks to meet legal discharge criteria and ensure effective control of chemicals in the restriction list. On the progressive level, the Foundation members should be able to apply advanced water treatment methods to address the wastewater issues. Lastly, on the aspirational level, no waste should be generated at all. I've shared earlier that petrochemical industry is one of the industries that generate difficult to treat wastewater. In this section, I'll share with you what are other sources of challenging wastewater. But before we do that, let us take a step back and look at how industrial wastewater is typically treated. Clean water goes through the industrial process and becomes contaminated as wastewater. After that, it is sent for treatment. The first step of treatment, also known as the primary treatment, physically removes the large particles such as suspended solids and oil and grease. Next, the secondary treatment step, comprising of the biological treatment methods, reduces the biological and chemical oxygen demand by the action of microbes. Finally, the tertiary treatment step uses membrane processes to remove the remaining dissolved solids and salts. But what happens if the biological treatment fails to remove some of the non-biodegradable organics? What options do we have? Well, we can either send it for direct incineration, discharge if paying tariffs is possible, or perhaps we can try to treat it. But what are we trying exactly to treat, and why are they difficult to deal with? Petrochemical wastewater consists of hydrocarbons with extremely stable cyclical and aromatic ring structures that cannot be broken down by the action of microbes in the bioreactor. Dye chemicals are engineered to be robust and bind strongly to fabrics. Likewise, pharmaceuticals are very stable compounds that will persist for a long time in the environment. Paper manufacturing produces lignin, a complex polymer that lends its rigidity to wood, which is challenging for biological treatment methods. All of these chemicals are known as recalcitrant or hard-to-degrade organics, which are characterized by high toxicity and stability with low water solubility and bioavailability. In some cases where recalcitrant organics are high, there are already industry players using different kinds of AOP, such as ozone, hydrogen peroxide, xanthan oxidation to deal with the wastewater. It can be used before the biological treatment to increase the biodegradability, or as a polishing step to remove the recalcitrant organics. In some cases, where the recalcitrant organic levels are too high or the COD levels are too high, it may make more economic sense to further concentrate the waste stream to increase the calorific value before sending it for direct incineration. So on average in Singapore, it costs around 300 to 400 Singapore dollars for each cubic meters of wastewater incinerated. I'll share with you some basics of advanced oxidation processes in this section before we look at some interesting AOP technologies. Advanced oxidation processes are termed as advanced because they are highly accelerated oxidative reactions. All AOP technologies involve the generation of some form of radical to initiate the oxidation reaction. The hydroxyl radical is one of the radicals that has high oxidation potential. Recalcitrant organics react with the hydroxyl radicals to form biodegradable organics, and they will further react with hydroxyls to completion to form water, carbon dioxide, and inorganic salts. So at this point, the waste is considered to be fully mineralized and can be disposed of easily. Let us look at how each of the AOP technologies stand when we put them in a technology readiness level versus chemical oxygen demand level. We first look at a group of technologies under high technology readiness level and low COD. They are mainly hydrogen peroxide and ozone-based AOP. Reagent costs and energy consumption are important considerations. This group of AOP technologies might not be suitable to deal with high COD levels owing to the high operating costs. They are typically used as a final polishing step to remove low levels of remnant recalcitrant COD after the biological treatment step, and they are used rather widely in the industry. The next quadrant consists of technologies such as pulse plasma, microwave, and electron beam oxidation. These technologies are extremely effective in dealing with recalcitrant COD. However, most of them are still in the lab or early pilot stage. This brings me to the last quadrant of technologies with high technology readiness level and has the capability to deal with high levels of COD. And they are usually also cheaper compared to direct incineration. Electrochemical AOPs is a class of promising AOP technologies which generate hydroxyl radicals via oxidation of water at the anode. Amrit from Indra Water will be sharing more about their proprietary electrochemical technology later. Dr. Oriana from Aquacycle will share more about how microbes can oxidize organics with bioelectrochemical treatment technology. UV or photocatalytic AOPs are efficient in breaking down organics. Zach from H2 Nano will tell us more about their reusable photocatalytic AOP. Wet oxidation elevates temperature and pressure to sub or supercritical regions to destroy organics. Professor Matthew will be sharing more about his work on catalytically enhanced wet air oxidation. These groups of technologies are promising to deal with high recalcitrant COD and organics. Today, I'll be sharing with you 5 other promising AOP technologies for your consideration. Superoxide radical oxidation is a relatively cheap chemical reagent-based AOP currently piloted in several locations across Europe for petrochemical wastewater and groundwater remediation applications. It is particularly effective against ring-structured and halogenated hydrocarbons. The superoxide radical is the strongest radical found in nature and can be generated in situ by a proprietary mixture of off-the-shelf chemicals at high pH. The superoxide agent is applied directly to the wastewater, opening up the organic chains for further and complete oxidations to PPB levels. It is a rapid method taking only minutes to hours and can remove up to 99% of the contaminants. Notably, this technology can also be applied to soil remediation and sludge treatment. The only drawback of this technology is that high pH at pH 11 is required for efficient application, and the superoxide radicals is rather sensitive to aluminum parts, so they would prefer stainless steel or plastic parts for the material of construction. Next is a UV catalytic based technology currently being piloted in chemical and pharmaceutical applications. It is effective in dealing with phenolic and polymeric compounds. The UV interacts with reactive chlorine species to generate hydroxyl radicals for oxidation. Instead of breaking down the complex organics to completion, the reaction can be controlled precisely by IoT to polymerize and convert to a precipitate, which can then be filtered away with relative ease. It is 75% cheaper compared to incineration, and no additional chemical reagents are added in the process. However, this technology requires a long residence time and is only suitable for small batches. The third technology is a hybrid adsorbent and electrochemical oxidation technology. This technology is already deployed at full scale in several locations with various applications around the world. It is effective in dealing with dyes and BTEX chemicals. The contaminants are first adsorbed by graphite-based adsorbents and oxidized by electric current. The hydroxyl radicals are first generated at the anode, and secondary radicals can be generated from chlorine-based contaminants. This process does not produce any sludge and produces only low levels of byproduct. Little maintenance is required and only 1 day per year. The drawback here is that hydrophilic contaminants are absorbed rather poorly, and process does not work well above salinity levels above seawater. Next, we have an electrochemical oxidation technology applied to pharmaceutical, petroleum, and landfill leachate. I would like to highlight that this technology is capable of handling COD levels of up to 1 million ppm for pharmaceutical wastewater. It can be used to remove key pollutants like aromatics, azo, and perfluorinated compounds. The innovation of this technology lies in the titanium oxide electrodes. Instead of the common TiO2 electrodes, a more stable Ti407 electrode with 40% higher oxidative potential is used instead. It operates in a similar fashion as any other electrochemical oxidation, generating hydroxyl radicals at the anode. The electrodes are extremely stable even in acid and alkaline conditions, with up to 3 years of electrode life. Overall, it is 80% cheaper compared to direct incineration. The only drawback here is that this technology is unfavorable for low TDS with trace pollutants. Lastly, we have a type of wet oxidation process known as supercritical water oxidation, which can be applied to pharmaceutical, textile, and defense industries, treating key contaminants like pharmaceuticals, detergents, and perfluorinated compounds. The wastewater is being charged into a vertical reactor and raised beyond the critical point of water above 374 degrees Celsius and 221 bar. At this point, the organics becomes super soluble and can be easily oxidized, while the inorganic salts becomes insoluble and precipitated out in solid form. The OPEX values are half the cost of incineration, and the carbon footprint is 5 times lower compared to incineration. However, the system CAPEX and OPEX are relatively high, and the energy consumption is around 200 to 250 kilowatt hours per cubic meter of wastewater. In this section, we'll take a quick look at the patent landscape for using AOP to treat industrial wastewater. In terms of patent filing activities, the top countries filing for AOP patents are China, USA, South Korea, Japan, and Germany. In our analysis, we found that 1,292 inventions were filed worldwide from a period of January 2010 to May 2020, of which many patent owners are Chinese entities. Many of the patents are filed in China, indicating that this is a very big market. Nevertheless, the competition is also stiff, as there are many Chinese entities who have filed for patents in China. When we look at the patent owners from China, we realize that many of the patent owners are research institutes and universities, potentially indicating that AOP technologies are in the development stage. It is also likely that a lot of ongoing research needs to be conducted to address specific type of wastewater. From our findings, we're not able to tell if there are any key market leaders in AOP. The technology providers offering AOP solutions varies from MNC, startups, SMEs, and universities. Sinopec and Siemens Energies are MNCs that focuses on using wet air oxidation to treat produced water from the upstream of the petrochemical industry. Exine Water Technologies is a US-based company that has filed several patents in electrochemical oxidation. Forward Plasma is a plasma technology startup that uses carbon or electric arc to generate plasma to break down organics. If you are considering China market or any other markets in Asia, you may want to consider partnering some of the technology providers I've shared earlier, or AOP tech providers who will be sharing about their technology later to explore commercial opportunities. Before I end off, let us do a quick recap of what I have shared so far. In this presentation, I've briefly shared about 5 promising AOP technologies. A superoxide radical technology with high oxidation potential generated from a proprietary mixture of reagents. An IoT-enabled catalytic technology which precisely controls phenol polymerization reaction for precipitation and physical removal. A method that absorbs contaminants for direct oxidation by an electric current. A novel electrode that has higher electric potential compared to conventional TiO2 electrodes. And last but not least, the supercritical water oxidation technology that oxidizes contaminants at high temperature and pressure. Each of these have their own pros and cons and suitability in different application areas. Feel free to reach out to us if any of these technologies interest you. In conclusion, I've touched on market drivers and trends. There's a growing market to treat industrial wastewater despite disruptions by COVID-19, driven mainly by the rise of industrial activities and tightening regulations. There are many wastewater treatment technologies out there that address this wastewater problem, one of which is AOP, which I've touched on extensively in this presentation. Our patent analysis have shown that there's a huge market in China. However, it has also confirmed that there are a large number of competitors, as many of them have filed for patents in AOP technology. Because of that, it makes more sense to collaborate with existing technology providers rather than reinventing the wheel. Thank you very much for your attention, and feel free to drop me a message if you'd like to discuss any of the featured technologies.
Okay, thank you, Ethan, for the presentation. So I think I mentioned earlier that we'll be launching a white paper on some of the findings. If you're keen to receive a copy, please indicate your interest in the feedback form that will be sent out after today's webinar. So next up, we will have Professor Shane Schneider, who will be presenting on opportunities and challenges of advanced oxidation processes for industrial wastewater. Prof. Shane is the Executive Director of the Nanyang Environment and Water Research Institute, also known as NUWI, at Nanyang Technological University. He possesses 20 years of experience researching on identification, fate, and health relevance of emerging water pollutants. So let's welcome Prof. Shane.
Okay. Hello, I'm trying to turn on my screen, but let's see. Okay. Hello, everybody, and I'd like to thank IPI for the kind invitation to share a few words with you today. I think Ethan did a fantastic job on his presentation. I wish I could do so well when I give lectures on AOP in my classes, but what I thought I'd do today, I'm just going to talk about some of the things that I've seen over the last 20 years that are both opportunities, but yet there are some challenges, especially when we're dealing with complex matrices such as industrial wastewater. So I'm showing an example here. This was a site that I visited myself in Indonesia, and as Ethan spoke previously, dealing with textile dyes in particular. And while they were making good gains from biological treatment, in fact, we believe that we can design an advanced oxidation system that could, first of all, take up a much smaller footprint, but also produce better water and actually save money. So I want to talk a little bit about why I would make such a statement and how we can realize such gains. And indeed, across Southeast Asia, we heard about China. There's a lot of opportunity for oxidative and other types of remediation processes, such as this example from the United Nations environment of the pollution leaving the Philippines and Manila. So when we think about what could be in an industrial or even municipal wastewater, there are a lot of potential chemicals. They can be inorganic, such as metals, or organic compounds, such as pesticides or pharmaceuticals. But don't forget that in some industries, we still have to think carefully about pathogens. In fact, I serve on the World Health Organization Drinking Water Advisory Group, and we always advocate to think about the pathogens first. So I'm not going to go into all these different options, but I think you can generally bin water treatment into three major areas. You can either separate, like a membrane, such as a nanofiltration membrane or RO, Of course, we can use biological treatment, aerobic, anaerobic, lots of different configurations, and oxidation or potentially reduction. So these are our major categories. But as Ethan mentioned, and I'd like to hit home on, sometimes the combination approach, though it may be more operationally complicated, can see gains in total efficiency. And one I just want to mention now that I'm working on at NTU with NURI is looking at the potential for nanofiltration and using the brine or the reject water from the nanofiltration, which could reject most chemicals, contaminants, and then using that brine stream in the AOP process. Instead of treating the entire flow of water, maybe we can combine the nanofiltration or reverse osmosis and then treat the more concentrated chemical constituents with advanced oxidation. But everything comes at a price. You know, if we think about, you know, disinfection, obviously chlorine, ozone are quite good. When it comes to viruses, UV can be more challenging. But once we get into AOP, we're in a different world. But just to be aware that there are always advantages and disadvantages of the many types of oxidative processes that Ethan mentioned. Of course, if we go back, at least in my history, we were mainly using oxidation for pathogen inactivation. And what we've demonstrated is that once we begin to form hydroxyl radical or superoxide radical, we not only can kill bacteria or viruses, but we actually begin to extremely damage their membranes and their ability to survive. There have been questions raised about ultraviolet light and whether it's inactivating DNA damage, which can subsequently be undone by different means. But when we're dealing with a strong oxidant, there is no question that the pathogens at the right dosage will indeed be dead and unable to be re-inactivated. Same is true for chemical contaminant oxidation. And you've been using this slide, I think, for 20 years. Some of my first work with ozone and ozone hydrogen peroxide. But if we look at a water, just taking a very simple example of color, and we pass it through even a mild ozone dose, you can visually begin to see that bleaching effect. And that's happening because the chromophores within the organic matter, the aromatic rings and double bonds that give something color begin to be broken, as Ethan also spoke about earlier. Whoops, double. So I won't go into this. You know, there's various definitions, and I think, again, we already heard a lot about that. And here are just a couple photos. This is UV advanced oxidation reactors that I've worked with. On the left is one in the Netherlands in Amsterdam, and the one on the right is in Los Angeles. And the one in the right is actually treating water that's bound to be recycled back to drinking water, which actually contains a high degree of industrial waste as part of the source water. So what are the reaction mechanisms? Again, I really don't want to go into this in depth. I want to point some special attention to the idea of using free chlorine and persulfate in lieu of hydrogen peroxide. There's a lot of gains that can be realized, especially if you're in a situation where you wish to keep a chlorine residual after this type of AOP. If you're using a hydrogen peroxide or some other types of co-oxidants, you then have to quench those before you can add chlorine, which becomes quite expensive. So UV chlorine really offers some really unique advantages, and this has now been built. I'm going to show you a photo of the pilot, but has been applied at full scale in Los Angeles, California. And again, the advantage would be that once that water is treated with the UV chlorine advanced oxidation, it's actually using chlorine radicals as along with OH radical, but it also will still carry a chlorine residual after the reaction, which can be beneficial, and it dramatically lowers the cost. Chlorine is cheaper than hydrogen peroxide, more commonly available, and is extremely effective in advanced oxidation. So again, this has actually at this point been built at full scale in Terminal Island in Los Angeles. So it's working well. And actually, although people may think there'd be a lot of chlorine byproducts, it actually forms less byproducts than chlorine alone. So I want to talk about one of the big challenges that we've found with advanced oxidation processes, and that is process control. And that's what I'm going to spend, I think I only have another 5 minutes, but to give you a feeling that sometimes the trickiest part of an AOP is how do you control that AOP, especially if your water quality is changing. In a constant, reliable stream, if your COD is constant, maybe your dyes of interest are at a constant concentration, you may be able to set up a reliable set of operating conditions and just run. But that's not usually the case. And the challenge is there really are no online monitors that I'm aware of for hydroxyl radical, superoxide radical, chlorine radical. These species last for fractions of a second, 10 to the minus ninth of a second usually in their half-life. So what we begin to do is we developed a indicator and surrogate concept where we can look at specific types of compounds which may be unique in different industries, but you can do monitoring of some target compounds and begin to know whether or not those are directly, in this case, photolyzed, or whether you need to add hydrogen peroxide or chlorine and not have to measure every single chemical. And what we're showing here is how we group them. We have some chemicals with the UV-AOP process that are directly photolyzed. They don't even need a co-oxidant like hydrogen peroxide. Some that are in the middle and some that are highly dependent upon OH radical. So we must have the hydrogen peroxide feed. So we can use that information, we can begin to optimize the process, which is another question. If you're going to run a UV-AOP, how much peroxide do you need? And what we can show is that there are diminishing gains once we get to a quite high level of peroxide. So money can be saved if we can actually optimize that peroxide dose. So one of the ways that we do this is using optical technology or spectroscopy. On the left, we show a correlation between the different groups of chemicals and the prediction based on total organic carbon. And on the right, we show the same prediction based on ultraviolet absorbance at 254 nanometers. So the bottom line here is that we can actually begin to use online sensor systems to help us control this advanced oxidation process. Quickly, how about ozone? That's my second favorite. I've worked a lot on ozone over my lifetime. And one interesting application, just trying to show you the synergy, is when we begin to apply ozone ahead of membranes. Now, naturally, you may think, well, that's crazy to add ozone in front of a polymeric membrane. It'll destroy the membrane. But what we've shown is that at relatively low doses of ozone and ozone with hydrogen peroxide, we can actually reduce the fouling index or the flux decline. In this case, we're trying to recycle a brine to get higher water recovery. And a major problem in the water industry is microfiltration, membrane filtration fouling. That is the membranes that are used for particle separation. And again, we've demonstrated that at relatively low doses of ozone, we get a quite big gain in flux decline. The membrane isn't fouling as rapidly. This was done at full scale at another facility in Central California. And in full scale, what they realized was that they did indeed have polymeric membrane failure. There was no ozone residual reaching the membranes, but the problem is that online sensors currently for ozone residual could not measure at that low of a concentration. There's also interesting chemistry that happens when you begin to add powerful oxidants. You can begin to oxidize things like bromide to hypobromous acid. If ammonia is present, you can even form bromamine. So all of these can impact the membrane. So you have to be very careful at how to control that process. So one of my favorite ways to look at processes is by fluorescence. So what we show at the top left corner is water's intrinsic fluorescence. This is a stream of wastewater, and it'll naturally fluoresce. So these are not individual one chemical or two, but the water itself, especially high COD water, will have a great deal of intrinsic fluorescence. But as we add oxidants, in this case ozone, we can begin to see that pattern of fluorescence change in a very, very predictable manner. So we have looked and developed algorithms that use both UV-254 transmission or absorbance on the left of the screen, or fluorescence on the right. Now, fluorescence adds some big value because the linear range is longer and the correlations tend to be a little better, but it's really the dynamic range of fluorescence that gives it a big benefit. And what we're showing is the correlation of the oxidation of various emerging type contaminants, in this case, mainly pharmaceuticals, and how well we can predict them based on the fluorescence or UV patterns. And this is a way we can now control that ozone system. And for instance, if you're dealing with a water that may have ammonia, if you have nitrite has a 1-to-1 molar ozone demand. In other words, the nitrite will rapidly quench that ozone. So if you're adding hydrogen peroxide, you may never realize it's happening till it's too late. So our method provides one way of process control. Lastly, I just want to make sure that people realize that no good deed goes unpunished. As you begin to oxidize water, whether it's advanced oxidation or conventional, you will begin to form byproducts. And in this example, we are adding pre-ozone before the membranes, and we formed nitrosodimethylamine, which is standard of the WHO at 100 parts per trillion, California at 10, EPA 1 in a million cancer risk at less than 1 part per trillion. You can see that as we oxidize, we form a high level of this byproduct. So in a potable reuse or even discharge to a source water, you really need to think about those potential byproducts. Quickly, how does ozone AOP compare to UV? I'm not going to walk you through this, but the answer is they're very, very comparable. It depends on the dose of ozone, dose of peroxide, but essentially you can get very similar doses. So it doesn't matter which of the two you choose. There are benefits, especially if the water has color or UV absorbance, to go with ozone, but both will work fine. But also remember that pre-treatment is very important, and I don't have time to get into that. I'm about out of time now. This last slide here is just showing you that actually, when we say we're removing COD or we're removing pesticides or we're removing industrial chemicals, well, it's not quite true. Advanced oxidation generally is transforming. It's converting that carbon into something else. The molecules are changing configuration, but they're not mineralized. In the case on the right, we show with quite high doses of UV and peroxide, we get maybe 20% mineralized, that is conversion to CO2. The rest are all byproducts. And if we look at that with high resolution mass spectrometry, I'll jump through this, you can see very, very statistically significant differences in these waters. So it means that some compounds are being formed, those are byproducts, while other substances, hopefully our chemicals of concern, are actually being removed, but again, not really removed, but actually being transformed. And sometimes that transformation can lead to something potentially more dangerous than you started with, such as a case we studied with benzotriazole, a common corrosion inhibitor. When adding ozone or hydroxyl radical forms a dicarbaldehyde. So you have to be cognizant of the byproducts. One last example for the pharmaceutical carbamazepine. Again, as we add ozone at low doses, we see a very stable transformation product. In this case, that transformation product is BQM, which is known to be highly toxic. So just be aware that when you're applying these things, you do form some level of byproducts. So what do I see as the path ahead from my experience in 20 years in the industry? Well, one of the exciting areas will be combination approaches. For instance, ceramic membranes combined with advanced oxidation, whether it's ozone, ozone peroxide. But at NURI, at NTU, we're working on catalytic membranes. Those membranes will have the properties to form an advanced oxidation or OH radical based on molecular ozone conversion. And I'm excited to say we are always looking for partners. We are happy to be working with the Trident Corporation here in Singapore on electrocoagulation, looking at options for Fenton reactions, and then combining those with a ceramic membrane. And through our philanthropic efforts, we are going to apply the system to a quite needy group in Chiang Rai in Thailand. And part of this idea is, can we put the best available technologies at an economical price into the hands of the people that need it the most? And of course, key to the success will be online monitoring, Internet of Things, and real-time sensing and control. So I hope I left you quite rapid, but an overview of some of the areas that we can think about. And later, I'll stick around for questions. So thank you very much for your attention.
Okay, thank you, Prof. Shane, for your presentation. Next, Professor Matthew Hu Xiao will be sharing on his research on catalytically enhanced advanced wet air oxidation. Professor Matthew is the Director of Environmental Chemistry and Materials Center at NURI in NTU. His main research interests are in functional materials, nanohybrids, composites, environmental materials, and chemistry. Let's hear more from Professor Matthew. The floor is yours, Prof.
Thank you. So are you able to see my slides? I guess not yet.
Not yet.
Yeah. Yeah, good afternoon, ladies and gentlemen, and thank you, Karen, for that kind introduction. I'm also very pleased and grateful that Ethan and also Shane gave a very comprehensive discussion on the advanced oxidation. So today my talk will be on the catalytic enhanced wet air oxidation at ambient condition. So without further ado, and what I'm going to introduce is that just to show what the current activities and in the environment and the water domain. So the green part are non-water related, and the blue part are related to water. So today I'm going to give you two examples on the functional responsive material and how they going to be used for low cost and point of use drinking water purification. And just one slide, and then followed by the smart draw solute for osmosis, and that we can pre-concentrate some of the water, like just Shane mentioned, and before we go for a further process. And then finally, I will be moving on to AOP and mentioning briefly on our effort on the catalytic and ceramic membrane, and then before diving to the ambient condition and catalytic wet air oxidation. So, okay, this is just one slide about our stimuli responsive draw solute for osmosis. I'm not going to go into too much detail. We basically use the responsive or smart and the polymers, and either in the solution form or the gel form. And then the highlight is that we are dealing with a problematic and wastewater that not easily treated by reverse osmosis, and particularly those with very high salinity and the RO cannot deal with. And we can further deep concentrate and such waste stream before, and then we go for other process, other treatment. And we could also use for the water removal and for food and or medicinal or even in the protein extraction. We just remove the water in a gentle way. So, and then the second one is an example I want to show is that we have a cryogel, and a hydrogel for water purifier, and we are able to use the polymeric hydrogel that absorb water, and then after you gentle squeeze, you can treat it within 3 minutes. You are able to turn turbid and pathogen and contaminate and water into drinking water, and fulfilling the requirement of a UNHCR and emergency drinking water. So we can achieve 6 log on the bacterial reduction, and at the same time remove heavy metal and the turbidity. And then we only need actually 4 grams of a gel, and each time we need 5 minutes. And then we can reuse 30 to 40 times, and then we can, each of these 4 grams of gel, we're able to generate 15 liters of drinking water, and it's very low cost. And then when we actually file the patent, and we actually won quite a bit of media, and also in the scientific and community as well, some attention. So right now, this technology is being, we are trying to look for partners and to bring into the market. We already have prototypes and also a second round of prototyping, everything. And this is the example, Okay, so advanced oxidation. So Shane had just now mentioned about the ceramic membrane, catalytic membrane, and oxidation. So we actually, as a material scientist and a chemical engineer, so we synthesize the new materials and we try to integrate those catalysts into either on the membrane surface and also into the membrane body. So and then as the wastewater flow through, and then the foulant will be rejected, and then while the oxidant will be activated by the catalyst, and then even at the surface to prevent fouling, and then once the water enters into the porous membrane, and then and the micro in a macro or micro porous and then structure, and then inside we also have a catalyst and the oxidant being activated by the catalyst to form a reactive oxygen species and transform or mineralize the organic compound. And the interesting part is that we could also integrate this with, depending on what material we use, we could utilize photocatalysis, and Shane mentioned about the UV and the ozone and the UV H2O2. And we could also introduce an electrocatalysis in this membrane, depending on what material we choose. If it's if the membrane itself is electroconducting, well, we have a lot of flexibility to manipulate, and it depends on the needs of the in the industry. So just to very quickly to go through the example, and we were able to deposit in the lab scale and also in a relatively large scale of onto a ceramic membrane disc, and we can also or filter, or we can incorporate in the ceramic and the tubular ceramics, and then we have developed a range of new catalysts and the material, and we have also developed a non-line of sight coating, which is very uniform and throughout the membrane pore. And but we are keenly aware that we need a very strong foundation about the understanding of the chemistry and material science and the catalyst development, and in order for us to actually to move on to have some breakthrough, and also so without the mechanistic change, and very hard to have a breakthrough. So we spend a lot of time understanding the mechanism, and especially transforming intermediates are also very important, as Shane has already articulated. So now let's look at the catalytic wet air oxidation. So our interest is really on trying to develop a catalyst that will activate an oxygen in the air into a reactive oxygen species, but at a relatively low temperature, and also at hopefully at the ambient and atmospheric pressure. So and then we right now we have tested this concept with synthesized a range of nano catalysts, and then we have immobilized it onto membrane. And this is actually a simple configuration for how we do the test. So here is the membrane cell, and the feed water going through, and then we have control, and then the clean water comes out. So I think in the literature, or in industry, I think that most of the CWAO and requires a high temperature and a high pressure. So here we try to look at we have now able to show some results, and we use some one of the several of the dyes. Here is one of the examples. So for example, I just want to show. Okay, the video that does not work, but anyway, so this video, I mean, later on we have other video to show, but this video, what trying to say is that if we use a bare membrane without the catalyst, and then and we would not see we will not see the color change, but after we put the catalyst, and then the other side, and up, then the water and believe me, and it turns and the color is completely reduced. So okay, so I think I used a different wrong version. So let me just come out and try to find the one with the video. Okay, my apologies. And yes, okay. So now, so as I mentioned, and this is a very quickly, and you can see, and this is without the catalyst, and then the water still remains very much intact. And then if you use we just simply coated this catalyst onto the same membrane, and the water came out and clear. So so that's actually the membrane process. So I was thinking, I think, can we make it even simpler? So we say let's design a catalytic and air diffuser, because the aeration is also one way, and it's been used for water treatment, even for pathogen control, and also for smell, and to reduce for the odor and all that. So we just simply have an air diffuser. This is what we use, and then what we did was, and then we again treat this air diffuser and with the catalyst, and then with barely 10 minutes and the bubbling of air, and then this is original water. After 10 minutes, and the water became very pale. So this is what we have seen. So one of the things, and we can see, is that the total and the actually DOC removal, and if you just pure without the catalyst and membrane, and very little removal. But and then after we have a catalyst, and then the removal is more than about 95%. And then if you just use a membrane plus the catalyst and as a powder in water, it also have some good removal, but it's not as good as a membrane integrated. So here is if you just use aluminum and alumina and aluminum oxide and catalyst, and without catalyst, and you don't see a color change. And with the membrane, and I mean, 10 minutes you already see visible, and the color and start to diminish, and then 40 minutes is really much clear. So the powder also still work, but not less effective. So, and we also try the same thing, and we bubble the water into pathogen, I mean different bacteria, and those the water, and then we find out, and then if you without putting any catalyst, but somehow we are actually quite surprised. The green bar shows and still have some pathogen removal, but I mean not too as good as when we added the catalyst. When we use the diffuser, the air diffuser with treated with a catalyst or coated with catalyst. So with that, I think I would like to thank you for your attention, and especially thank Ethan for the invitation. And I would also like to acknowledge my research team, and at NTU, and also at NURI, and also the School of Material Science and Engineering. And we acknowledging the Smart Innovation Grant, Ministry of Education RE 2020 Innovation Grant, and funding directly or indirectly, and through PUB, and NEA, A-STAR, and several of our industrial partners. So and thank you again.
Okay, thank you, Prof. Matthew, for your presentation. In the next section, we'll be presenting to you 3 water tech startups which have developed different treatment techniques to address industrial wastewater. These 3 startups are portfolio companies of Imagine H2O, which is an international startup accelerator focusing on water technologies. We are happy to have Anna Marie Martin with us today to share with us more about Imagine H2O, as well as its program. Anna Marie is the program associate in Imagine H2O, where she supports the accelerator operations, including startup outreach, communications, and market research. Let's hear more from Anna Marie.
Thanks, Karen, for the introduction. I'll just share my screen. Okay, so hi everyone, my name is Anna Marie and I'm the Program Associate for Imagine H2O Asia. So I know Karen gave a very brief introduction on what we do, but just to provide some further background on who we are, Imagine H2O is a nonprofit that's based out of San Francisco with an office in Singapore as well. So our mission is to help empower people to develop and deploy innovation to help solve water challenges globally. So our flagship program is our accelerator, which is dedicated exclusively to helping startups and entrepreneurs in the water sector. So here's some quick statistics to showcase our record over the past 10 to 11 years, where we've helped a total of 150 startups, deployed more than 100 solutions, provided $1 million in funding, as well as helped alumni raise around $550 million in early stage investment. So as you can see, we work across a very wide range of water startups, including themes like network management and leak detection to water and wastewater treatment. So particularly what we've noticed over the past few years is that we are seeing growth in the number of startups in the themes of water and wastewater treatment, as well as drinking water access and delivery. So every year we have over 500 companies apply to our programs. So we run 3 programs in total, where in addition to our accelerator programs, we also have a global competition called the Urban Water Challenge that provides pilot funding for startups. So while the accelerator programs help the startups in a number of ways with things like mentorship and visibility, the Urban Water Challenge is focused primarily on funding support. Imagine H2O sees applicants from all around the world, but what I want to draw your attention to at the bottom left of the screen is this incredible growth that we're seeing for our Asia program, with a 35% jump from applicants from the region. So this is a very encouraging sign for potential water entrepreneurs, for existing ones to know that there is this budding water innovation ecosystem. Our program comprises of 4 key pillars. So first, we provide advisory and mentorship, where we connect our startups with technical, market, and investor experts to provide advice for them. Next, we have pilot funding support, which is usually modest, but is aimed at removing some of that sting that's usually associated with starting a pilot with a new customer and having to pay for that upfront cost. We also provide customer and investor access, where we rely on our ecosystem partner network to make introductions to utilities and manufacturing and industrial players in the region. And finally, we provide industry visibility for the startups, usually by showcasing them at major trade shows and industry events. This is a snapshot of our growing regional network. So as you can see, we have Enterprise Singapore, Suez, ADB Ventures, and Curita as our program sponsors. And for our program partners, we have PUB and SWA. And we also have more than 20 other ecosystem partners from the region, such as K-Water from Korea, SCG from Thailand, even a wastewater treatment operator from Vietnam. And one of the main benefits of being in our ecosystem partner network is that you get to be an early adopter of our startups' water technologies. So for our team, we have my colleague Kelvin and I based in Singapore, along with our key partner ESG, with the rest of the team based in San Francisco. And as you can already tell, our team is quite lean, which is why we have a sort of informal extension of our team, which is our advisory council. So this is a network of water experts that we rely on, especially during our evaluation process, when we make the open call for startups to apply for our program. So we work very closely with our advisory council throughout the year. And finally, I want to just very briefly introduce the audience to our 2020 Asia cohort. So out of over 100 applicants, we've selected 11 startups to be a part of our cohort. So these startups come from India, US, Korea, UK, and of course, Singapore. And all of them will be showcased at our demo day during Singapore International Water Week's virtual event in 2 weeks on November 19th. So if you'd like to learn more about the startups, please join us then. And lastly, before I hand over the time to our startups, I'd like to talk about a few ways that you can engage directly with us. So firstly, if you become an ecosystem partner in our network, you'll have early access to water innovations and startups, and you can also flag out your own innovation priorities, which we would look out for during our evaluation process. In addition, there are also program sponsorship opportunities available to dive deeper with us. And for mentorship, if you think you have expertise in the water market or in certain water technology themes, you can also join our council to help play a mentorship role for the startups. And lastly, if you visit our site and explore our portfolio of startups and you find an alignment with your company's needs, then you can always feel free to reach out to us so we can help to bridge that connection. And again, since we will be showcasing our 2020 cohort at SIWW, as well as Switch in December, these will all be really great opportunities to connect with them. So now I'll just quickly introduce our next 3 speakers for the event. So we have Amrit from Indra, who is part of our Urban Water Challenge competition in 2018, followed by Ariana from Aquacycle and Zach from H2 Nano, both who were part of the 2018 US Accelerator. So Karen?
Okay. All right. Thank you, Anna Marie. So for startup companies or aspiring entrepreneurs among the audience, you can reach out to Anna Marie directly if you wish to participate in their program. So let's now hear from the startups who will share more about what technologies that they have developed. So we've actually pre-recorded the pitches earlier, as some of these companies are operating in different time zones. One of them in the India time zone, one in US, and the other one in Canada. But the founders are present here today to answer some of the questions. So if you have any questions, feel free to type in the Q&A chat box. Okay, so first up, let's hear from Amit Om Nayak, CEO and co-founder of Indra Water.
Good afternoon. I'm Amrit, the co-founder and CEO of Indra Water. At Indra, we are pioneering decentralized wastewater treatment at the point of source and recovering this water for non-potable reuse applications. Our vision is to accelerate the transition to sustainable water management all across the globe. Now, before we move on to that, let us first look on how centralized municipal systems have been functioning till date. Whenever we think about that, images of very large pipelines, large pumping stations, massive civil infrastructure flood our minds. We all know that all this wastewater from different buildings, different houses, multiple industries, they're all pumped to a single large infrastructure for treatment. But this process is inefficient, not only because there are energy losses, but we lose a lot of water because this infrastructure is difficult to maintain. It also becomes extremely difficult for an operator, even if a plant is completely automated, to react to changing wastewater requirements. Sometimes, before we realize that something is wrong with the plant, a huge volume of water has actually passed through without getting the right kind of treatment. But that is pollution happening right there. A huge amount of solid sludge is also generated by these plants. And most of the time, this sludge cannot be directly reused, as a lot of it is due to the industrial effluents that have come into the plant. Indra has been trying to solve a lot of these problems right from the word go. Our solution is compact and smart, and our solution is electrically driven. Our patented physioelectrical process is effective and efficient and performs coagulation, advanced oxidation, and disinfection of domestic and industrial effluents, and we recycle this water for non-potable reuse applications. Our systems are plug and play. Because we do not use any chemicals, and we have eliminated the complete logistics chain associated with that, we're able to save 40 to 50% in operating costs and 35% or more on life cycle costs. Because our systems are electrically driven, our chemical processes or our electrochemical processes happen instantaneously, thereby dramatically reducing the retention time required in our systems. Hence, our systems are 75% lower in footprint. Now, that is a lot of productive area available for industries. It adds to economic viability of our projects. We recover 95% of the water that we treat. And this water is sometimes fit for direct use in industrial processes. We do not use any chemicals. And we are still able to meet all the Central Pollution Control Board norms laid down in India. Our systems are designed and built for mass production. Conventional systems generally take about 6 months to build and commission and about 2 more months to set right and stabilize the output. However, we are able to do this in 30 to 40 days even today. Our smallest systems are 5,000 liters per day and our larger integrated modules are about 200,000 liters per day. And whenever we need to meet larger throughput requirements, we can stack up these modules and keep increasing the number. All our systems are automated and smart. We collect a lot of data in terms of water quality parameters and in terms of the functioning of the electrical equipment in our systems. This helps our systems to dynamically respond to changing water needs and in turn provide optimal water treatment which helps us save money in the process. It also helps us achieve predictive maintenance and remote troubleshooting. We are primarily operational in the real estate market, that is sewage treatment in the domestic as well as commercial buildings. In textiles and dyes and paper and pulp, we're treating effluent water. And this is our primary target market in India. And this market is $4 billion in size. And it is growing at more than 15% year on year. That is a massive opportunity. We are egged on forward by the stricter regulations and mandates for setting up STPs and ATPs in the country. Rise in cost of fresh water and the huge gap between demand and supply is a massive opportunity for us. Even in the Southeast Asian market, the whole market is growing at 8.8% year on year. And less than 20% on an average of the wastewater generated is treated in our target segments in Singapore. Now that again is a great opportunity for us. As you can see from this graph, that we are very competitive with respect to all the other players in the market, and our 10-year life cycle cost for a sewage treatment plant has been displayed here. All values are in rupees per meter cube as absorbed in our projects in India. We are primarily operating in the sub 2 MLD category in the country. Some of the projects that I would like to mention are a 75,000 to 100,000 liters per day biorefinery plant that we set up, and we're able to recover almost all of the water for non-potable reuse applications as well as industrial processes. 50% cost reduction, 75% reduction in footprint, and 75% reduction in sludge has been achieved. We have also deployed plants in lakes for water reclamation for the purpose of irrigation, especially in the city of Hyderabad. In some of our textile projects, we have been able to reduce the cost by 50% and obtain 75% more water. And the water that we are supplying back at the source can be directly reused in the sensitive jeans washing process. All our activities have resulted in saving 200 million liters of water, and this number keeps rising. 500,000 people have been positively impacted by our actions. We have worked with a lot of large clients and partners, and we continue to work with the best in the industry to forward and to promote our technological prowess as well as partner with them for improving our work. Imagine H2O has been instrumental in this process. Our team consists of myself, Krunal, Abhijit, Aditya, and Shriteja, and we have a lot of good experience from the likes of Amazon, Tata, Bosch, and we bring in all these expertise into quicker deployment of our solutions in the market. We were the recent recipients and we were the winners of the Urban Water Challenge at the World Water Week in Stockholm. And we have also won the Millennium Alliance Award very recently. Our plan for expansion in Southeast Asia involves partnerships and collaborations in technology, operations and maintenance, and also deployment of projects. We are also open to technology licensing because it is very important to understand that local solutions, local problems require the involvement of existing local players. And we believe that our technology can be improved with their feedback. So we are willing to work with all the players out there in the local market to efficiently deploy solutions that are more economically viable and help us make water recovery and wastewater treatment more sustainable in the long run. So I'm open to more questions. At the same time, before we move on to that, I would like to thank IPI for giving us this massive opportunity to showcase our work and help us become a part of this massive circular economy in the entirety of Southeast Asia. Thank you.
Next up, let's hear from Dr. Oriana Breger, CEO and founder of AquaCycle.
Hello, my name is Oriana Brecher. I'm the CEO and founder of AquaCycle. AquaCycle is headquartered in San Diego, California, and we provide technologies and services to treat some of the most challenging wastewaters generated in food and beverage production. Specifically, we address these ultra high strength wastewaters. So these are going to be wastewaters that only represent about 20% of the total volume out of the plant, but 80% of the cost relative to managing and disposing these wastewaters. Now, the concentrations of COD, or chemical oxygen demand, and TSS, total suspended solid, may be 100 times to 1,000 times more concentrated in organics than what you see in a typical city sewer. And so this poses challenges relative to disposal in that every client needs to meet their permit for whatever municipality that they're operating in. And they're going to be charged usually per kilogram of organic carbon and per kilogram of TSS that they put down the drain. These costs can add up anywhere from $1 million to $2 million per year per facility just to manage these very small volume, high concentrate waste streams. Now, if for whatever reason the company is not allowed to discharge to the sewer, the only other option right now is to haul these wastewaters off-site and land apply, which is costly and also has an environmental footprint. Now, these wastewaters are only going to be increasing as many companies are starting to decrease their overall water usage in production. That means the concentrates of wastewater coming out of the plant continue to go up and up. So this problem is only getting bigger. And that's where AquaCycle comes in. We provide an on-site wastewater treatment solution as a service to customers. Usually we're saving them anywhere from 20 to 60% against surcharge costs and or land application costs. We validate the technology already in commercial environments with customers like Mars Wrigley and Anheuser-Busch. And we provide real-time remote monitoring and controls, which really helps to catch issues before they become problems and alleviate the requirement for a full-time 24/7 operator on site. We can catch anything before it becomes a problem and make sure that we call a local service provider to do whatever maintenance or emergency response may be required. That means minimizing any production shutdown for the client. Now, what I'm showing you here is a breakout of the actual product. And so what we offer is the bioelectrochemical treatment technology, or BET, which is that little black box that you see in the image. Now, each one of those reactors is about the size of a standard car battery. They're quite small. And we stack them together like Legos inside standard size shipping containers. They're a 20-foot or 40-foot container, depending on what the customer requires. The number of reactors that we have operating in hydraulic series, for example, 40, will define how much carbon we can remove in a given hydraulic residence time. And then we have multiple parallel treatment trains that will accommodate the volume at the customer site. Now, this is a bioelectrochemical process, and we use naturally existing bacteria already present in the wastewater and or sourced from the local environment to run the process. We bring these bacteria in with the wastewater that we want to treat, and they start to form biofilms or fixed films on the internal surfaces of each reactor, those little vertical cylinders that you see in the breakout there. Now the bacteria attach to those cylinders and they start using those surfaces as a way to breathe or a way to respire. And in that respiration process, they're giving up electrons. We harness those electrons, we move them across the circuit, producing DC power. Now, the faster we move electrons away from those bacteria, actually, the faster we're making them breathe. And when they're breathing fast, that means they're eating fast. And so the more electricity that we produce actually leads to faster treatment rates. Now, the power that we generate can actually be used to offset the power demand of our system. We aim for net neutral. In some cases, with high COD applications, we can be net positive. And so you see the picture here. That's actually an example of one of the systems we built for a small brewery here in Southern California. We have manufacturing established already in South Korea, Tijuana, and here in the United States. Here are some examples of some of the installations that we've done with various customers, both in the US, multiple states, as well as in Tijuana, Mexico. And some examples of data sets that we've generated. This is with a confection customer. You're looking in the bar chart there. The bars represent the percent of COD that we removed within a 4-hour hydraulic residence time. And the numbers reflect the total amount of COD that was removed in that hydraulic residence time. So we can actually remove up to 50,000 parts per million in 4 hours with only 12 BET reactors operating in hydraulic series. We're also generating useful power in this process. 1.6 kilowatt hours per kilogram of COD was recovered in this process. And that equated to around 22 kilowatt hours in a day, which is about 50% of the total power required to run the system, which was about the size of a Fiat in relative footprint. We also have some of the lowest secondary biomass production values relative to other technologies. Now, how we would stack up technology to technology in terms of full kilograms of COD removed per day, we offer some of the fastest treatment times on the market, the lowest secondary sludge production that you can see, as well as some of the best energy recovery efficiencies relative to conventional anaerobic treatment. And we're doing this in hours as opposed to days. And so we're very excited to work with our global clients, always seeking customers that are looking to solve issues with high sugar, high solids, and high surcharges wherever they're operating in the world. And we're always also seeking channel partners and local participants to provide that on-site service to our customers on a global scale. And we do have an A round open, so if you're interested to learn more, please do contact me. My information is there. And thank you very much.
Okay, last but not the least, let's hear from Zach Young, COO and co-founder of H2 Nano.
An emissions control solution for a variety of industrial wastewater settings. And excited to be able to have the chance to share some more about it with you today. So H2 Nano's solar pass technology is a passive, sunlight-activated water and emissions treatment technology. So what that means is we can apply this technology for both treatment of dissolved organics in water as a enhanced or polishing treatment step, eliminating things like hydrocarbons and surfactants from the water. It can also be applied for treatment and containment of emissions and odors in these same wastewater streams, treating things like hydrogen sulfide and sulfurous compounds or volatile organics that are in the water. And so we've designed this technology to be a modular, scalable system that we can apply in a variety of industrial wastewater and remediation settings. And I'll tell you a bit more about how that integrates. So what H2 Nano has is a passive advanced oxidation treatment. And to tell you a bit more about how that contrasts with conventional oxidation, chemical oxidation technologies, as you will know from the conversation today, have a high treatment strength. They can eliminate a lot of recalcitrant organic contaminants. However, these are very intensive chemical and energy input processes. And so a solution that doesn't require those input intensities would be beneficial. However, biological treatment processes, which may be more passive or moderate input, have a lower treatment strength and in fact can generate some of these odorous compounds as well. And as a whole, don't address the full spectrum of treatments that may be required. So what H2 Nano has done is brought the merits of these two together in our solar pass technology. So it has a high treatment strength. We're able to eliminate the same kinds of contaminants that chemical oxidation can take care of. In fact, in some cases in a more targeted and accelerated way. But it does this with a sunlight activated process where we're using a direct green sunlight power to do that treatment without intensive electrical inputs. And this passive and low input process ultimately reduces the chemical input burden. It doesn't have a substantial waste stream or in some cases any waste stream coming off of the system as a reusable material. And all of that drives down treatment cost and improves the scalability of this process, especially in industrial wastewater settings. So the way that SolarPass works is through a material and process innovation that enables us to deliver that passive treatment approach. So the treatment occurs through the water surface, where we use sunlight as our energy source. And H2 Nano's proprietary materials float near the surface to absorb that sunlight and uses that to passively and with high strength apply that advanced oxidation to contaminants in the water. So the technology is what we call a photocatalyst. It generates from the water and dissolved oxygen itself a variety of mixed radical species that then ultimately are what are delivering that oxidative treatment to the contaminants in the water or some of the odorous compounds that we intercept and treat at the surface of the water before they evaporate from the pond. So the SolarPass technology is a platform that can be applied in a couple different manners. One of those is a conventional, once through treatment process where either upstream or downstream of a current treatment application or as a standalone process, we can accept water, perform the treatment with our treatment material, and then at the end of the process, we recapture for reuse the catalyst material. And the only thing leaving our treatment process is fully treated water that meets the specification required, using process controls where we can monitor the amount of energy input from the sun and adjust our dose and mixing of the material to deliver the treatment needed. We can also deploy this in pond, so treatment using H2 Nano's in pond booms and containment structures to be able to deploy our treatment material directly to treat or cap and contain emissions in a conventional treatment pond or lagoon setting. So this works in a variety of different industrial treatment applications, either in process water management where we're treating waste streams or reuse water in oil and gas, mining and energy, in wastewater treatment streams that may be found in textiles and manufactured goods, and aquaculture and agriculture or chemical goods production. So a variety of waste streams where there are organic contaminants or odorous compounds to eliminate. And also looking at this as a environmental controls technology where we might be applying these just on odor and emissions reduction for different water sources, managing emerging contaminants or in stormwater and leachate, those applications that might be more conventionally looking at from a municipal or government treatment application. So H2 Nano's SolarPass has a few benefits. One of them are enhanced treatment, so we can deliver a new treatment capability for these persistent organics and odors in this advanced oxidation process in a new and passive way. That passive treatment process is greatly improving the treatment economics. We have a very simple infrastructure and process equipment to do this treatment, which reduces the capital expenditure, as well as reducing the operating expenditure by reducing those chemical and electrical inputs. And it's safer and more sustainable. We can deliver that same kind of treatment that would be otherwise requiring hazardous chemicals and requiring a large environmental footprint. H2 Nano's technology has been applied in a couple different settings, one of those being treatment of dissolved organics in a oil extraction process where we were able to use just one day of sunlight to take what would have been months to years potentially of holding time to eliminate aquatic toxicity from some of the processed water. As well as applying it in a setting where we've done treatment to eliminate and reduce some of the odorous compounds from outdoor holding ponds by being able to get rid of over 70% of the emissions from some of those pond systems by deploying our technology. So H2 Nano is looking for new treatment applications. We have a ready team of world-leading experts in photocatalysis. We've deployed some of the largest outdoor treatment processes for this kind of technology that we know of. And are looking forward to being able to examine how we can apply that for your treatment application, or look at new process integrations where partners may be looking for enhancing their current service offerings or being able to integrate H2 Nano's technology to further enhance biological and chemical treatment processes that you're using today. So please reach out. My contact information is here, or you can find us at our website, h2nano.ca. Thanks so much, and I look forward to your questions.
Okay, so this concludes the last presentation of today. We have now come to the Q&A section. So can all the presenters please turn on your camera so everyone can see you. So we are very happy to have the founders of Indra Water, Aquacycle, and H2 Nano with us, despite the time zone difference. I know Dr. Oriana and Zach, it's probably very late in Canada as well as in the US. So if you have any questions for them, please feel free to just type in the chat box. So actually before the event itself, we have a couple of questions for the audience. So I thought I'd like to first address some of this question. The first question is actually directed to Prof. Shane. You covered a little bit about real-time monitoring earlier. So this question is actually related to that. I'd like to seek Prof. Shane Snyder's view on effective ways to bridge the gap between real-time monitoring and dynamically optimizing treatment processes to effectively neutralize heavy metals and chemicals. You have any comments?
Well, yeah, I guess just a general comment. So in the case of heavy metals, we have been developing algorithms around this fluorescence type signal that we can demonstrate the coagulation, whether it's working well or not. We haven't specifically done it for heavy metals, but it's something we want to look into because we are looking at electrocoagulation with Trident Corporation here in Singapore. So we have that in our plans for the future. But it's a good question.
Okay. The second question, what is the best method to handle high COD, high TDS wastewater? Is there a general method to separate organic and inorganic components from aqueous stream? Prof. Matthew, would you like to take this question?
Yeah, sure. Again, very good questions. I think this is one of the probably most difficult in the waste stream and that we can encounter. High salinity and high organic content. So I guess we do have some general rules, and basically it's a separation technology. So they likely to form a different combination of technology, but for example, start with the filtration to see whether we can separate the salinity and the organic by size. And the other one, of course, and after that, you can have a different way. Depends on whether you want to harvest the organic or just destroy the organic, or whether you want to valuation to extract the metal, and they have a standard way. So it's challenging, but there are ways of doing and dealing with this. And I mean, we really need to look at the water chemistry and the needs. And before we prescribe a process.
Okay, thank you, Prof. Matthew. Okay, this one is for Zach. How would you see H2 Nano system being deployed in Singapore, given the space constraint that we have? Also, how many times can the catalyst be recycled before replacement is required?
Yeah, both great questions. And I think that actually ties into one of the space questions that was presented in the Q&A. So H2 Nano's material, we have a few ways of deploying it. Some of them are the larger scale outdoor ponds where we're harnessing sunlight over a large area. We also have some ways that we can package the technology to use sunlight collection, say in rooftop units or in other deployment settings that we're currently exploring, as well as potentially augmenting it with artificial UV light that can be a source for the energy as well. In terms of the reuse of the material, typically it's rated on an overall treatment lifetime that we're using it for. So there'd be some periodic replacement, in the course of months for us to reuse it. And again, that kind of depends on the treatment setting it's being deployed into and whether, it's a more contaminated or less contaminated water that it's interacting with.
Okay, thank you, Zach. So this one is for Dr. Oriana. Oxidation of organics using microbial fuel cell has been researched for many years, but there are not many commercialized technology out there. What has Aquacycle done differently to make commercialization possible? Also, are there any challenges when it comes to scaling up the operations?
So yeah, scaling bioelectrochemical systems has been the challenge, and specifically being able to develop reliable, cost-effective cathodes in the bioelectrochemical systems. The approach that Aquacycle has taken has really been to focus on optimizing the dimensions of the system. So you lose efficiencies in any electrochemical system, the bigger your electrode gets and the farther the distance they are away from each other. And so our approach has been to really figure out what are those optimal dimensions so we can pass a critical volume, which is meaningful to the customers, without losing those efficiencies. And so instead of having huge electrodes and big tanks, we have small electrodes and a lot of small little boxes, and then we just multiply them, right, to accommodate that volume. So it's a very different approach than others have taken before. And then also, just being able to demonstrate the reliability and feasibility and manufacturability of cathodes.
Okay, thank you, Dr. Oriana. There's one question for you, Amit. Electrode preservation is one of the major challenges in operating electric-based wastewater treatment system. How does Indra Water Solution address this issue?
That's a great question, and in fact, one of the most challenging things in any electrochemical cell. There's no one single approach to do that. We use a very multi-pronged approach to deal with something like that. So it involves a lot of innovations in the powering mechanisms, the reaction controls, the design and flow patterns achieved within the reactor, and at the same time, even the choice of materials. For example, by switching or reversing the polarities, you're able to bring both electrodes into play and at the same time ensure that you don't allow any one electrode to get fouled or passivation to happen on any one of them. At the same time, even controlling microbubbling or the amount of effervescence of gases that happens in the different electrodes. You're able to kind of control the size of the flocks that are formed, because sometimes when you break down the flocks a lot, you end up preventing them from properly coagulating and rising up or going down. So that kind of ends up settling up because the gap between different electrodes is generally very low. So these are some of the areas. Apart from that, the different kind of materials and the choices on them and the amount of electric current that you pass in. For example, we're doing a lot of good work on advanced microelectrolysis. In fact, one of our engineers here, Sarthak Mehta and his team, have done some tremendous work on that. Now, in that kind of a scenario, when you're able to push down power requirements, which is also sometimes essential, it brings down the amount of passivation and at the same time thermal fatigue that happens to the material on the electrodes. So a lot of these approaches come together, precise control over all these factors to actually decide and enhance the shelf life of different electrodes. So that is one of the ways we do it, and we're constantly working on that.
Okay, thank you. There's one question on why are emerging AOP technologies not applied widely for treating difficult wastewater? Ethan, would you like to take that?
Sure. I think most of us here today can agree that water industry as a whole is rather conservative, and for good reasons, because the project sales cycle is long, and also adopting unproven technology can be quite costly if it does not work, especially we are talking about hundreds of thousands or millions of dollars of investments. So extensive piloting is required to get all these emerging technologies to kind of get it started, and this comes with another cost. Yeah, so wastewater itself, when as an end user, we consider it as like a cost center and does not really generate any profit. So this is something that the polluters usually consider as last thing, and they will just kind of get away with just doing the bare minimum in the past. But nowadays, there's the local regulations have become stricter and more stringent, as I've shared earlier. So we require more efficient technologies to meet this discharge criteria. And because of that, I'm seeing more companies open to take up some new technologies, be it from academia or startups like all of you to address some of these issues.
Okay, this one is for Prof. Matthew. For catalytic wet air oxidation, what is the energy required to pump through the membrane? Is it similar to RO or nano?
Yeah, a good question. So it really depends on what membrane you use, and we could start with a nanofiltration. We could even use a microfiltration, and but you see the example we show, and we have One that is akin to is a hybrid, and we have a nanofiltration and a rejection scheme, and we also macrofiltration and substrate. And but if you look at the air diffuser, it's really, I mean, there's virtually no energy is required, just very, very little energy. So we don't have any resistance, just an air bubbling. Basically, that once you bubble through the catalytically treated membrane, and you generate the reactive oxygen species.
Okay. Okay, this question is for Dr. Oriana. Is BET feasible for high-strength wastewater from quick service restaurants, for example, like McDonald's, KFC, etc.? What is the treatment cost per meter cube of treated water?
So, great question. The answer to the first question is that it depends. So we're able to accommodate fats, oils, and grease up to around 300 parts per million. But beyond that, we require dissolved air flotation ahead of us. Otherwise, the fats, oils, and grease will start to come into the internal structure of our system. So depends on how the restaurant's operated and how they're discharging, what the grease traps look like, etc. Relative to cost, that also depends. So where we operate on a service model, and so that service includes the use of the equipment, the real-time monitoring and controls, as well as emergency response for any local issues that might be going on. So that's all sized based on what it is that we're treating. So what's the chemical composition and concentration? What's the quality that we have to achieve? How clean do we have to get the water? And then, ultimately that defines what it is that we're installing. So monthly fees really are more associated with pounds of BOD, COD that we're going to be removing within a volume range that we're going to be processing with the customer in cubic meters per day. And then that can be a fixed fee or a variable fee, depending on how the customer wants to structure the contract. So it all depends.
Okay. I think we have a final question. I think this is for Amit. The question is related to comparing between chemical coagulations with electrocoagulations. So the question goes like this. What are the different types of electro materials used and the durability? What is the durability and economical feasibility between chemical coagulation and electrocoagulation?
To answer that question, you do not have a single, formula that electrode composition or a particular choice of electrodes where cathodes and anodes are going to work with all kinds of wastewater. And unit economics does play a very important role in how we decide the shelf life of electrodes. For example, as Professor Shane had very extensively spoken about use of titanium dioxide, which is absolutely brilliant in these situations. However, sometimes, especially because we are operating in countries like India, where unit economics is very important, so we do have to go for materials which are, cheaper and at the same time more easily available. So you might have to go with even aluminum or iron or different alloys or other metal oxides, and maybe adsorption media. So that plays a very important role in deciding different, combinations of electrodes that are used. At the same time, as I mentioned, because we are slowly trying to move towards non-contact microelectrolysis, this will make it a lot more efficient even with simpler material. Because ultimately, it is not just the effluent treatment plants with the paying capacity which are going to use these systems, but it's also the sewage treatment systems which need to come into the main stream. So that is the primary thing with respect to the electrodes. With respect to the comparison, yes, chemical coagulation as observed in the projects in India, many a time due to manual error and improper pH control, a lot of chemical dosing is done, which is kind of eliminated in these electrically driven systems and the other solutions that have been presented here. So there is a very huge difference in the optics that is observed generally, and as everybody has seen, in fact, in all the presentations here, you are almost in the range of 40 to 50% savings everywhere. So that kind of answers that first part of the question.
Okay, thank you, Amit. So I think there are many other questions, but they have all been answered by the speakers through typing. So I guess that's the end of this Q&A session. We'll be sending out a feedback form to you at the end of this webinar, so you'll be greatly appreciated if you can fill it out to share with us, to let us know how we're fair in organizing this webinar, and also, most importantly, how we can do better in future events. Also, if you'd like to receive a copy of our white paper on industrial wastewater treatment, please indicate your interest in the feedback form as well. So hopefully that gives you some incentives to fill out the feedback form. Okay, once again, I'd like to thank all the speakers, Ethan, Prof. Shane, Prof. Matthew, Dr. Oriana, Zach, Ami, as well as Anna Marie for joining us. Most importantly, I'd like to thank all the audience for your time to attend this webinar. We look forward to seeing you again in our future events. In the meantime, please take care, stay safe, and have a wonderful weekend ahead. Thank you. Bye.
Thank you.
Thank you, everyone.